Google has built a microservices architecture on top of the internal container management system known as Borg. This microservices architecture has existed for many years, and the services on this architecture communicate over an internal protocol known as Stubby. Borg and Stubby are tightly coupled to Google's infrastructure. It would not make sense for Google to open source Borg and Stubby, but Google has worked with the open source community to develop open source projects with the core functionality of Borg and Stubby. And these projects are known as Kubernetes and gRPC. Sandeep Dinesh works on the Google Cloud Platform as a developer advocate. Our conversation explores how a client application request from an app like Gmail would communicate with Google servers, where the request would be handled by a network of microservices that are running in containers. And we break down the taxonomy of what is in these services and what is in these containers. So we also talk about where the Google Cloud Platform is evolving and how it offers a competitive, differentiated model from Amazon Web Services. This is a really fascinating show about Google's infrastructure, how people can build, quote, microservices architectures, and many other things. I want to take a moment to thank you for listening to the show. If you enjoy the show, please share it on Facebook or Twitter. Tell your friends. That translates directly to growth and revenue for this show. And as the revenues grow, I will reinvest money into Software Engineering Daily and grow it more. You can help keep the flywheel spinning by sharing with your friends and helping us grow. And I'm always really grateful for this. And I want to know any feedback that I can do to help the show improve. So thank you for listening. And after a quick message from our sponsor, we'll get on with this episode. Podcasting full-time is a great career, but if I ever return to the normal world of work, Hired.com is where I will start my job hunt. Hired.com removes the frustration of searching for a job. You just fill out your profile and the jobs come to you. Facebook, Uber, and Stripe are a few of the companies that are hunting for engineers on Hired. Go to hired.com/SEDaily to try it out and get an extra $1,000 signing bonus, just for using the URL for Software Engineering Daily listeners, which is hired.com/SEDaily. So if you want to try it out, go to hired.com/SEDaily. The demand for engineers is higher than the supply. And on hired.com, that translates to higher salaries and happier careers for the engineers who find a job on Hired. I used Hired to find a job before I became a full-time podcaster. And the experience was so good because Hired connected me with a talent advocate who worked with me to find a job that was a good fit. And the talent advocate answered my questions about negotiating salary and finding remote work, which was something that was really important to me at the time. So check out hired.com/SEDaily and get a $1,000 signing bonus upon finding a job, which will be a great job that will give you the respect and the salary that you deserve as a great engineer. So check out hired.com/SEDaily. It would support the show. And now let's get on with today's episode of Software Engineering Daily. Sandeep Dinesh is a developer advocate at Google. Sandeep, welcome to Software Engineering Daily.
Thanks, Jeff, for having me.
I want to talk about how to build microservices. And in order to do that, let's start with the application level itself. So let's take a prototypical app like Gmail. When I open up Gmail in my browser, there is an application container spun up somewhere on a Google server, and a session opens up between my browser and the Gmail application on the Google container somewhere on Google's infrastructure somewhere. Give me an idea of what that container on the Google server consists of, and what is the type of communication that is taking place between my browser and that containerized application.
Sure. So I'm not 100% sure what's going on in Gmail specifically, but that's a pretty good example. It's a very complicated application that's doing a lot of things, right? So when you're saying a container spins up somewhere in Google, it's very similar to the idea of App Engine, where a container spins up, handle your request, and then spins down. So that would be communicating over something like HTTP or HTTP2, and it would be serving you whatever's in its cache, right? That's the first thing it tries to serve you because we want to have the fastest speed possible. And then it's going to be making network request calls all the way back down the stack to various other services to get your mail, get your chat, things like that, and then propagate all that information forward to you as well.
So explain what kinds of services that Gmail container might be communicating with, because obviously not everything is taking place within that one container itself.
Exactly. Yeah, so Gmail is a very interesting choice or example to start with, because when you talk about mail, it's a very stateful application, right? If you're accessing your email on your phone and your laptop at the same time, you have to be able to see the same worldview. And it won't make sense if you have one message on one device and not on the other. So consistency is pretty important there. So at Google, we have a database called Spanner, which is a globally consistent SQL-like database. And this is one of those services, right? So Gmail would store all of its messages on this Spanner database, and it wouldn't store it internally. So with a monolith, you would store kind of everything in that one big stack. But with Gmail, any of these containers, right, that spin up, a different container could handle the request from your phone, and a different container could handle a request from your laptop. And so, but both of these talk to the same Spanner service to give you the same consistent view of your inbox. And at the same time, they might do a REST request call to the Hangout service to show the chat messages as well, right? So these are two very separate services that are owned by separate teams, but they're both propagated by the same front end. So it feels like one application, even though multiple teams might own each part.
So is a container spun up to service every session that I have, or are there containers that are handling multiple sessions, and then when a certain number of sessions have been reached, another container spins up to scale the overall service? Yep,
number two for sure. Multiple containers one container per user would just be kind of overkill, because you kind of lose a lot of that shared resources, right, between the different, like one network connection on one of our servers cannot possibly be saturated by one user, right? So it doesn't make sense to spin up a new instance or a new container every time someone connects. So we do have, if you look at something like App Engine, this is exactly how it works. Once it reaches a certain threshold where performance can no longer be met, right? So either milliseconds of response time or CPU time, whatever the criteria is for that team, then they spin up a new one, and then all the new users go to that new one. And then once the load goes down, you can just spin them back down. So that gives you kind of that horizontal scalability.
When a container gets spun up on the Google architecture, it is running on Borg, which is the Google container system. And these containers can communicate with each other across a protocol called Stubby. Is that correct?
That is 100% correct.
So for listeners who are unfamiliar with these technologies, could you give a brief explanation of what Borg is and what Stubby is?
So people might remember way back, like 10 years ago, Google started contributing code to the Linux kernel that lets you run isolated environments, right? So what we call containers today. So this is because Google has been running containers in production for the past 10 years. And when you're a company that has, over like hundreds of thousands of servers and hundreds of thousands of processes running on these servers, managing that stack becomes extremely complicated, right? You can no longer manually log in to a rack to configure something or deploy something. You have to treat it like a giant computer that you're programmatically interacting with. And this is kind of what Borg was designed to do. So it's a container orchestrator and scheduler that runs all the services at Google, right? So a team will write a container, and then Borg is what actually babysits it, what scales it, and what makes sure it's up and running in multiple clusters around the world. And then, of course, you have all of these systems, right, all running in multiple clusters around the world. They're scaling up and down. Now communicating between those two, right? Something like Gmail needs to be able to communicate with Spanner to get the email, right? It has to be able to communicate with Hangouts to get the chat messages. And you need a very efficient protocol to communicate because you have all these containers spinning up and spinning down. And if you start saturating your network stack with RPC requests, like really fat RPC requests, then you're going to run out of networking very quickly, right? So that's why Stubby and protocol buffers were invented to have a very lean and mean RPC framework, so all these services can talk to each other in our clusters.
Borg and Stubby themselves, they could not be open sourced because the technology of Borg and Stubby is tightly coupled with Google's internal architecture. Yep. But both Borg and Stubby now have open sourced versions of the technology. Kubernetes is a project that's very similar to Borg, and gRPC is, I think, an even more recent project, and it's similar to Stubby. So let's first talk about Kubernetes. How do you describe Kubernetes?
So yeah, I would definitely describe it as the third generation of cluster management at Google, right? So like you said, Borg has a lot of internal legacy. It would not make sense to open source it. We would have to strip out a bunch of things and people will be like so confused why we did XYZ, right? And it would be impossible to contribute source code back upstream because it just wouldn't make sense to a lot of people. So Kubernetes was started as a completely from scratch reimplementation of a cluster management system, but leveraging all the things that Google has learned over the past 10 years of running production level containerized systems, right? So you can think about it as our third generation cluster manager that's 100% open source. And that's basically what Kubernetes is in a very high level, right? So it's a system that allows you to orchestrate your Docker or app-C containers on a cluster.
We've done some shows about Kubernetes, but I think it's a really important project, and I want to rehash just even some of the things that I've touched on or the guests have touched on in previous episodes. So some important components of Kubernetes are the application itself running in a Docker container, and then the pod, which the container runs in, and then the replication controller. Explain these three units and how they interact: the application, the pod, and the replication controller.
Sure. So I'm going to add one more to that explanation, which is the service, which I think is a very critical piece. But I'm going to start all the way down at that Docker container. So the container is what I like to call the subatomic particle of Kubernetes. So you can think about it as your application logic or your glue logic, whatever you have, the code that runs, right? That's your container. Now, the atomic particle, right, the atom of Kubernetes is definitely the pod. So a pod can be one or more containers that work together. So typically I see people deploy a container as a pod. But the reason why we have pods is sometimes you want multiple containers to live and die together, share the local namespace, things like that. So a good example is a proxy that does some sort of gateway logic or something like that has to live very close to your application code, right? So you want these to be scheduled together. You want localhost to be the same between the two. So now your application can just hit localhost and that proxy can do whatever it needs to talk to the rest of Kubernetes. And now you can use that proxy in all of your different pods with different application containers. And now you don't have to rewrite your code or something like that. So a pod is like the atomic particle of Kubernetes. So now you have this pod, you have to actually run it on your cluster, right? And so this is where replication controllers, or more recently in Kubernetes 1.2, deployments come in. And a deployment is basically exactly like it sounds, right? It's a way you run your code on your cluster. So you say, I want to run this version of this container, and this is my pod, and I want 10 copies to run on my cluster. Now, your deployment will spin up something called a replica set, which is very similar to a replication controller in Kubernetes 1.1. And this replica set will ensure that 10 copies of your code is running in the cluster somewhere at all times. So what this really gives you is even if a server goes down, even if a process crashes, the replica set will detect that and automatically spin up another copy somewhere else in your cluster. So you have all of these like 10 copies running. Now you want to scale up. So what you can do with the deployment is simply scale up the deployment to 15. And you now do a deployment, the second deployment, and now it'll deploy to 15. And let's say now you want to update that deployment to the next version. So now you do the third deployment and you say, I want version 2, right? So now you have 3 deployments, one at 10, one at 15, and then one at version 2 with 15. And the cool thing about a deployment is you can just go back. Let's say version 2 had a bug in it. You can easily deploy the second deployment again, just roll back to it, and everything works as expected. You're no longer panicking over, oh man, how do I roll back? What do I do? What do I like roll back my Git? What do I like? None of that happens anymore. You kind of just roll back to version 2 of your deployment. And the deployment has a very, very rich history, so you can just go through and pick which one you want, and you have a very good log of what you did in your system.
Do you also do canarying and A/B testing within the abstraction of a deployment?
Exactly. So one deployment would be one, so a deployment would not have 2 versions running inside of it. But how you do something like a canary or an A/B test is you simply launch another deployment, right? So you have your let's say your prod deployment and your canary deployment. And your prod deployment has 15 copies and your canary has 1, right? And then once the canary starts working, you then flip the prod deployment to that new version, and then you flip your canary to that experimental version, right? So you'll roll both up as you feel comfortable. So you would have multiple deployments for these multiple A/B tests.
So when you said the term service, did you mean
Yes.
deployment? Is that the same as?
I did not. Right.
Okay.
So that's the last piece, and I think one of the most important pieces of Kubernetes, and it's really what lets microservices work in your cluster. So we talked about canary and A/B testing and things like that. Well, you have all these deployments that are running pods somewhere in your cluster, right? 15, 10, 4, who knows how many. It makes no sense for the users of your service to memorize where these pods are running in the pod IP addresses. So services act as a stable IP address or a stable endpoint that will route traffic to these variable pods, right? So you can have like a service for your database, a service for your front end, a service for, let's say, a machine learning analyzer or something like that, right? And so with the Kubernetes system, these services are exposed over DNS and IP, so all your different microservices can find them and talk to them without worrying about how many copies or whatever is running under the covers. So it's something like a canary. The same service would actually load balance traffic to your prod deployment and your canary deployment. And because you have 1 versus 15, you can see how much traffic is going to be split between the two, right? But your users only hit one service, which is pretty cool.
So the abstraction of the service is basically a router.
Yes.
Okay, interesting. So at this point, is there any worth in differentiating between the term microservice and the term service? Or I mean, I guess the service in terms of the abstraction that is a router, and maybe the microservice is just the whole topic that we're discussing, or?
Yeah, I would say the service is more like a technical term, where microservice is more of a philosophical term. Yeah, it's just the word for the thing in the cluster is called a service, and it so happens that microservice also has service in the name, right? They both interestingly similar. Like a service enables you to have microservices more easily, but they're not dependent on each other in any shape or form.
So yeah, I think microservices is one of these things that's, I don't know, it's kind of like DevOps, where you know it when you see it, rather than fixating some definition on it. I don't know. What are your thoughts on that? Do you have a concise definition? It's been a while since I asked somebody the question, like, what is microservices? but I don't know. Maybe it's a worthwhile question to occasionally ask.
Yeah, one of my friends, he loves to say the two pizzas rule that Jeff Bezos loves quoting, right? So if your team can be fed with two pizzas, then it's a microservice. I like saying if your app does one thing and one thing well, then it's probably a microservice. If it does more than one thing, it's probably not, right? But again, it's super complicated, very personal subject, which is kind of weird, right? You never think computer science is a personal thing, but it definitely is. I like this. If someone can understand the code, like you hire someone and they understand it, what's going on within a week, and they can rewrite it within 2 weeks, that's probably a microservice. Now, if it takes them like 2 years to like re-architect this giant thing, that's probably not a microservice, right? That's probably something else. So it's basically, can you understand it and can a small team manage it? That points you in the right direction, but I, again, don't think that's the definition. It's a very complicated and touchy subject, right?
I think it's also the answer to the question of how do we scale and mature our systems? So the discussion of a monolith versus microservices, I think the discussion gets framed as if there are many options for building a system, but really it seems like the only modern option, or the best modern option, is certainly over-indexed towards, okay, you start with a monolith, you build an MVP because you've got a small team and everybody can understand the monolith, and then over time, if your product scales, your team is going to scale, and then you advance into quote-unquote microservices.
I would have to disagree with that.
Really?
Yeah.
So I guess this is the Kubernetes story, because you can get microservices from day one.
Exactly. With something like Kubernetes, it kind of abstracts all of that complicated, oh man, now I have to spin up 4 VMs, and each VM has a different like version of Node.js and Ruby and Java, and like I had to manage all this like ops stuff. Screw it. I'm just going to write everything in Scala and like launch my monolith, right? What you had to do that because it was just too much ops overhead to like try to do microservices from day one. But with something like Kubernetes or a higher level pass like Days or whatever on top of it, you don't have to worry about that stuff anymore, right? So it gives you that operational freedom to do microservices from day one. And now it becomes more of a, does it make sense for my team to do microservices or not? Not like I can't do microservices because it's too complicated, right? So now if it's like I'm doing this spam filter in Python and my front-end code in Ruby and a back-end thing in Go for it, right? In the past, you'd be like, okay, well, the best language for all three of those is Python. I'm going to force everything to be in Python. Now you don't have to do that anymore. It's just so much easier to do microservices that it becomes an option, right? It's on the table now.
Fascinating. Okay, so when I was talking to, I think it was either Brendan Burns or Kelsey Hightower, I did these Kubernetes interviews recently, and it kind of got the impression that that is an inevitability. What you are describing is an inevitability. We're going to get to the point to where it's easy to flip a switch and turnkey solution microservices day one, the Ruby on Rails of microservices. But the impression I got talking to them is that it is still a little bit too hard. There's still no, in Ruby on Rails, it's just like Rails new, you get everything and you got a monolith and you did it with one command.
Yep.
Are there still too many steps to incentivize people to just do this from day one?
That's a really good question. I would have to say it depends, which is the worst answer in the world. But so someone who has a lot of Kubernetes experience, who's very DevOpsy, I think they could do it from day one. But I would say the majority of developers don't fit into that category. They're someone who knows their wheelhouse really well, and they can spin up a Ruby on Rails app like that and get MVP out the door very quickly, right? Now, for someone like that, I feel like Kubernetes is still a little bit too low level, right? It gives you not enough scaffolding to start, right? So Ruby is a great language. Rails is the scaffolding around it that lets you spin up those MVPs and spin up those even production level applications very quickly. With something like Kubernetes, I think it's like the Ruby, right? It's the programming language for your cluster. Now you need some sort of scaffolding around it. And if you look at the ecosystem today, you can see a ton of startups building platforms on top of Kubernetes. And I think that is going to be the triggering point. One or two of these startups is going to hit critical success, and that's going to be amazing, right? That's what I see kind of happening is that platform on top of Kubernetes, those platform as a services that are still open source and run the open source stack all the way down. That's going to be what enables the majority of developers to start microservices from day one.
I also get the sense that there is a more abstract discussion here to be had about the types of companies that people are building these days. I think of Web 2.0 as being very epitomized by the lean startup, iterate to the local maxima, to the local maxima, to the next local maxima, and this rapid iteration as opposed to some of the more ambitious things that are coming out these days where you say, okay, I'm going to put my foot down. I'm going to do this thing that's really hard and it might take me a lot of time, but I am taking the deterministic calculus-based approach and going for this big, bold goal, and I don't care how long it's going to take me. And I think of the latter approach, the more recently popular approach to really, really hard problems that might take a longer time, as more closely associated with okay, day one, we're going to build on the thing that's going to give us the best long-term support. But maybe that's a more abstract discussion. So, okay, let's talk about things that are more a little more focused. So I watched this talk where you quoted Martin Fowler, and Martin Fowler said, the biggest issue in changing a monolith into microservices lies in changing the communication pattern. And when we go from communicating within a single monolithic app to a network of services, there are communication changes that we need to make. And you already discussed this a bit with Stubby. And now I want to get into a discussion of gRPC. So when we're talking about communication within a network of services versus communication within a single monolithic app, what are the changes that we need to make?
Right. So just to give some more detail, right? So what happens when you move a monolith to a microservice is what was once a function call, right? Just a normal method that, puts something on the stack, whatever, now becomes a network call. And a network call has a latency factor, a unreliability factor. Who knows? That service might be down, right? All this complication comes into play now once you're going over the network and talking to someone else's service, right? You don't own that. Your team does not own that other service. That's the whole point of microservices, is that independence. So now you have to think about all that stuff. And even before getting into technology that helps with it, like gRPC, you have to start thinking at a different level, right? There's a lot of stories, even inside Google, where it's that service will never go down, so we don't have to error check. We don't have to provide a sane default. And then that service goes down, right? And then it's everything breaks and teams scramble. And it's wait, what? That core service can go down? And so at Google, we have some things called basically we simulate disasters, right? And I think a lot of people should do this in their own companies as well, like the chaos monkey. What happens if a data center just gets hit with a nuclear bomb, right? And this service does not even exist anymore, and that team is now dead. Okay, what the heck do you do, right? Does your service still run? Maybe, maybe not, right? So that at that very high level of abstraction, you had to change your thinking pattern into not trusting anybody, right? I mean, it's a really weird thing to say, but you can't trust the network. So that really changes your application development mentality. And then the other thing, of course, is performance. So you can't do doing a million network calls, opening and closing TCP sockets over and over again. Bad idea, right? And that's where technology like gRPC can totally help. So gRPC, for the listeners who don't know what that is an open source version of Stubby, and it's actually very, very, very close to what we use internally at Google. So Kubernetes was a complete reimplementation, but gRPC is actually pretty close to what we use internally. So what it lets you do is optimize that network calling piece, right? So instead of opening and closing multiple TCP stuff, open and closing TCP sockets, you can just have one persistent socket and do streaming over that one socket. Things like that, that really helps you build those microservices.
Yeah, okay, so let's talk about that in a little more detail. How does a remote procedure call like gRPC, how does that compare to communication over REST?
So if you look back into like what REST was invented for, right? Representational state transfer, right? It was meant for stateless services, which is very close to what a microservice is, over the web, right? So when I think about REST, I was doing REST with PHP way back in like 2008, but like, what's that, jQuery and things like that. And it's really easy to build AJAX systems, right, with REST APIs. And the cool thing about REST APIs is they're self-describing, right? Get, put, post. It kind of makes sense. You can just read the HTML. You can read the path and understand what's going on, right? And I think that's why REST just took off compared to XML or whatever. Where let's not even talk about XML. Let's just not talk about that because it's just complicated, right? JSON and REST was so easy that like everyone started using it. And the problem with it is it wasn't ever built for high performance, right? It was built for ease of use, at least in my opinion. Now, JSON parsers and things like that have gotten ridiculously fast. But if you're now doing what was once a function call, right, over the network, you might be doing thousands of these per second, right? And now all of a sudden, JSON and REST don't scale to that level of performance that you need. So what do? Now you go back in time to the 70s and you take a concept called remote procedure calls and you bring them back into 2016. That's what you do, right? So remote procedure calls were this thing when you had like client server way back when, where the client was this thin client who couldn't run any code on itself, right? So it would do a call to a giant mainframe that would process the data and then send the result back. And that's what RPC was back in the day. Now it's a way for our microservices to all talk to each other. So you have these microservices talking to each other over JSON REST. It might make more sense to do it over a RPC framework like gRPC.
Software engineers are always looking to automate their work. Software automation lets us get more done with the same number of resources. Investment automation works the same way. Wealthfront is an automated investment service that relies solely on software to acquire and manage client accounts. Traditional investment services have many humans in the loop, advising clients and taking fees. The problem with these older advisory services is that the advice that these services are applying is often so systematic that a computer could give the same answer, or an even better answer. Wealthfront takes a new approach with software-driven automated investment that provides better returns through software engineering. Go to wealthfront.com/SE daily to get a special offer for our listeners. $15,000 managed for free when you open your account. Don't pay commissions and account fees. Maximize your gains with Wealthfront's Set It and Forget It investment automation. Check out wealthfront.com/SE daily. It would support Software Engineering Daily, and it would also introduce you to the world of automated investment, so you can see if you like it or not. Wealthfront.com/SE daily. Thanks to Wealthfront for sponsoring the show. You've been a loyal sponsor, and we really appreciate it. Now let's get on with the show. And gRPC uses protocol buffers. So these are a language-neutral way of serializing your data. So think of JSON as also kind of language neutral at this point. It also kind of serializes my data. So for people who have never heard of protocol buffers, or even if you've heard of a protocol buffer but you don't really understand what it is, can you talk about protocol buffers in more detail? Explain what it is, why it's more efficient than JSON.
Sure. So, like you said, JSON and protocol buffers are two different serialization formats, right? And all serialization does is it takes data and puts into a format that can go over the wire and then turn back into that data, right?
Ones and zeros.
So, with protocol buffers, and so just to be clear, gRPC is actually serialization format neutral as well. So you can put in JSON through a gRPC call, or thrift, or flat buffers, or whatever you want. Now, you have to write the code to do that. Right now, gRPC only supports protocol buffers out of the box, right? So what does protocol buffers give you? Well, it gives you a lot better compaction compared to JSON, and a lot better serialization and deserialization performance. And the reason why is it's binary, right? And it's doing this all, and it's so let me rewind a second, right? So with JSON, it's basically a JavaScript object notation, right? So curly braces, the little tag, and the object, right? And it makes it super easy to really describe any sort of data structure. Now with protocol buffers, you have to write something called a .proto file. And this .proto file describes what kind of data you're going to send, describes how you're going to serialize it. And because you have this .proto file, we're able to make serialization and deserialization much faster because we know exactly what you're going to send over the wire. And because of this as well, you're able to compress everything into a very tight binary format, again, to send over the wire and then deserialize very quickly.
Right, because the more that we know about the structure of our data, the more compactly we can serialize it, because the more we can understand the patterns of that data. Exactly.
And I think CoreOS did a really great blog post where they basically compared the performance of JSON REST over HTTP 1.1 versus gRPC over HTTP 2. And it was mind-blowing just how much faster gRPC was at sending these things back and forth. And the cool thing about something like gRPC is because, again, you've described that data in the .proto file, you can actually use something like a reverse proxy to actually expose a JSON REST gateway and a gRPC gateway on the same port. And again, CoreOS has a great blog post about how you do this as well.
gRPC takes advantage of some of the HTTP2 features, as I understand.
That's right.
Can you talk about how HTTP2 contrasts with HTTP1? What are the things that gRPC is taking advantage of?
Sure. So for people who don't know, HTTP2 is the new HTTP protocol. Well, I say new, I don't know. It's been around for years and for now, right? So it's what Chrome and Firefox and Edge and all these browsers use to talk to websites. And Google, Facebook, Twitter, they all support HTTP2. Nginx supports HTTP2. So what the heck is it, right? HTTP 1.1 and 1.0 were really designed for the web of yesterday, right? When you make a request to download an image, that's all you can do. And in vanilla HTTP, you can only do one request at a time, right? So when you have a modern website which has thousands and thousands of things, you can see how slow that would be. Now, with modern browsers, they do something called pipelining, where they can open like 6 connections at once. Ooh, right? A whole 6 connections. Well, with 1,000 stuff on your page, that's still going to be really slow. With something like HTTP2, you can do asynchronous download of the whole page. You can do things like bidirectional streaming. Again, with HTTP1, it's request response. So you have to resort to things like WebSockets or long polling, things like that to get streaming to work with HTTP1. With HTTP2, it's built into the protocol. And again, this allows you to do different things, and I'll get into that in 1 second. And the last thing is HTTP2 is binary, right? With HTTP1, It's all plain text. You can literally telnet into a HTTP server and then type in commands and hit enter and see what's coming over the wire. And it kind of, you can read it, right? It's human readable. Human readable is great, but the performance suffers because of that, right? With HTTP2, it's all binary. So with those three things, you get a ton of performance, but the protocol is still the same as HTTP1. It still gets inputs and posts. Now, what gRPC uses is all of those things, right? With the asynchronous nature, you can just have one TCP connection open and do multiple RPC requests over that same pipe. With something like bidirectional streaming built in, now you don't have to do request response. You can say, every time there's a new user that hits my website, I want to do X, right? And it can just stream those requests straight to the server without opening and closing a request every time. And then finally, with the binary format, it works perfectly with protocol buffers, right? You're not wasting any space trying to serialize this into a text format.
So gRPC also has some really good support for mobile devices.
Yep.
Could you put this into context of the conversation? Like, give me an idea of how my mobile device would communicate over gRPC with a backend service. And also, sure. I mean, I'd love to hear about like how HTTP2 fits into the discussion of mobile device support.
Sure. So gRPC supports Objective-C, Java, and C#. So that's the three major mobile platforms, Windows Phone, Android, and iOS, right? And so what this lets you do really is take advantage of those features. So like your microservices need fast performance, right? And they need low network usage. And your phone also needs the same thing, right? Your phone can just be an extension of your system. When they open your app, they want it to load quickly, and they don't want it to take a lot of battery life, and they don't want it to take a lot of their very precious and expensive mobile data, right? So the same advantages that a microservice has are also applied to the phone. So it's faster, it's more battery efficient, and it takes less network usage, which is great.
So what about the container-to-container communication? How does that work with gRPC?
Yeah, so it works the exact way that you would expect, right? You put in the IP or the DNS name and the port, and you're good to go. And this is where I think something like Kubernetes and gRPC, they play really well together because you can just give it the name of your Kubernetes service, and then that service will actually do the round-robin load balancing, find the appropriate pod, and then connect those two together, right? So now your microservices can talk to each other over gRPC. And gRPC has a lot of those error-checking stuff built in, right? It'll throw different errors that make sense. I think another problem with using JSON REST is it throws HTTP 1.0 errors, right? Like 403, 404, 500, 502, whatever. Now, these were built for the web. They weren't really built for microservices. With gRPC, you can actually do custom error codes and things like that that make a lot more sense. So now you can have your microservices actually respond correctly with the correct error code and things like that. So now your services can talk to each other and understand what's going on.
And as we're now getting into the discussion of the intersection of Kubernetes and gRPC, or just basically the services and the communication layer that they're using, could you contrast how Borg and Stubby are used with how Kubernetes and gRPC are used? Are there any significant differences between how the internal Google architecture has evolved to communicate versus how the open source translation of that infrastructure has evolved?
I can try. So I feel like someone like Brendan Burns would definitely know the answer better than me because he's worked on both. And I'm just a user of Kubernetes. But from what I can tell, and I might be totally wrong on this, is Borg bound ports very differently than Kubernetes. So Kubernetes has a virtual IP, the idea of a virtual IP space, right? So every single pod gets its own IP address and its own range of ports. So it can do whatever it wants with whatever, right? versus I think Borg, what it would do, it would, again, I might be completely wrong on this, it would bind ports on the host itself, right? So now you fight for ports and things like that, and you had to do port mapping and all this complicated logic. And I think that's the one big difference between something like Borg and Kubernetes. And of course, Borg has a lot more mature tooling and a lot more mature configuration options, right? It has more mature schedulers, more mature resource constraints and things like that. That Kubernetes is still, people are still building that for Kubernetes, right? So I think that's the big difference between what we have internally and what we have externally. We think the Kubernetes method of the virtual IPs is a lot better. And then if you look at gRPC and Stubby, they're pretty much the exact same thing. The one big difference is, of course, gRPC is able to leverage vanilla HTTP2. Stubby had to do a bunch of custom TCP or UDP stuff to get it to work, right? With HTTP2, it has all these features built straight into the stack, so you don't have to mess with the lower level stuff, which is great.
So talking about how Kubernetes or just the microservices architecture helps us get things rolling at a company more smoothly. Microservices get us things like continuous deployment, scalability, security. Explain how microservices make some of these application characteristics easier to attain and why Kubernetes is useful for this.
Sure. So I think the big reason why it makes these things easier is because it very clearly splits the development and the operations pieces from each other, right? So with something like DevOps, you are responsible for the full stack, right? The developer doesn't just write code and then throw it over the wall and say, hey, operations, please run this, right? That's not that's a very bad pattern to fall into, because now you don't have ownership over your production environment, which leads to very bad habits for your development team, right? And then your operations folks be like, no, we don't accept any new updates, right? And then you have this fight between the two teams. And then DevOps was supposed to solve all of that because one team owns the whole stack. Now, with something like Kubernetes, what it lets you do is have, again, one team that manages the cluster, right, and provides the Kubernetes service itself to the developers. And now the developers can own the whole stack, but they don't ever SSH into machines or manage the machines themselves. Instead, they manage the Kubernetes deployments, right? So let's say you need more capacity. Now you can just grow your cluster, and for the developer, it just seems like they got more servers. They don't have to care about those servers or how they were set up. With something like Google Container Engine, you just add a server, and then boom, you get a bigger cluster, right? And now on the developer side, what it lets you do is, because you're not worried about the raw infrastructure anymore, you're treating this cluster as an entity, as a single entity that you interact with the Kubernetes API. You can do things like rolling updates and deployments and horizontal scaling, things like that, without having to own the whole stack at the same time owning your whole stack. If that makes any sense at all.
No, it does. And so as you're talking about the usability here and how the different teams fit into this, like the DevOps idea, I think it's relevant to talk about the SRE role at Google. Which, that's the software reliability engineer, right?
That's right.
So there was a book that came out about this role pretty recently. Could you explain how does Kubernetes reflect the usage of Kubernetes, or perhaps the usage of Borg at Google? How do these things reflect the role of the SRE and how the SRE interacts with the different engineers at Google?
Sure. So SRE is a pretty unique thing that Google has. Now, as far as I know, they don't do everything. Actually, I'm 100% sure they don't manage all the systems. To get SRE, quote-unquote SRE support, is actually very difficult. So SREs are extremely methodical in what they do, and how they do it, right? Basically, the idea is they will support your application only if it's a certain level of good, right? Otherwise, you can just write junk code and then say, SREs, please maintain this. And they definitely don't want to do that. They want to support well-written, scalable, and performant code, right? And so what they can do is, and again, I don't know too much about SREs. Actually, one of my coworkers is going undercover as an SRE for a year to learn more about exactly what they do, which is going to be awesome. Paul Newson, he's going to take a very deep look at exactly what's going on behind the covers of being an SRE. So just so we can talk about it and let our customers know exactly what we do as Google, right? But again, they maintain and run those systems, those critical infrastructure systems for the rest of Google, right? And these are the things like Megastore or things like that all Google services depend on. And that's really what SREs do, is they make sure that these things are up and running. And unlike a traditional ops team where they're not software engineers, they don't know what's going on, they just kind of run the systems as is, SREs really allow experimentation to occur, right? So it's okay if there's downtime as long as it never, ever, ever happens again for the same reason, right? And this is very similar to like the Facebook culture and things like that as well, where you want to, if you break something, fix it fast and make sure it never breaks again for the same reason. And that just, so your systems become more and more and more robust as time goes on.
I want to wrap up by talking about some about the Google Compute platform in relation to the rest of this conversation that we've had. So this is the Google Cloud offering. I'm not exactly sure what the GCP, that is basically the top level expansion or explanation of the thing. That's the kind of the Google equivalent of Amazon Web Services. So many listeners in the audience have been working on systems with Amazon Web Services for many years. And I've talked to people, the vast majority of people who are deploying to the cloud have been using AWS, but that's just because AWS has been focusing on this for a long time. As I understand, Google has a pricing model that is usually cheaper for most people, but even so, some people are resistant to change simply because they understand AWS quite well and they understand the APIs, they're comfortable with it. Mm-hmm. If I am building a new application today and I want it to have Kubernetes and microservices, how does GCP, the Google Compute Platform, how does it give me an experience that is so good that I will build my app on Google rather than Amazon, even if I have experience with Amazon?
Yeah, for sure. So I think at Google Cloud Platform, we kind of take a slightly different approach than our competitors. Something like Kubernetes, again, is 100% open source, right? So you can run it on AWS, you can run it on Metal, you can run it on Azure, SoftLayer, whatever you want. And it's the same experience. Now, what we give you, right, is something like Google Container Engine, where on something like AWS, you have to manage those machines yourself, right? You have to spin up EC2 instances, install Kubernetes, do things like that. Whereas in Container Engine, we manage that for you. So we just give you a cluster and you start going, right? And a lot of people like this because if for whatever reason Google drops the ball, right? We stop being competitive with everyone else. Well, you can just migrate off to someone else and there's no lock-in, which is really awesome. Another thing is, it's really hard to explain over a podcast, but the performance that we give you is pretty mind-blowing, right? You can spin up something like 1,000 Linux VMs in under 5 minutes. I'm not sure if you can do that on any other cloud provider. You can do things like hot grow persistent disks, known in the AWS world as an EBS volume. You can hot grow them, right? So if you have a 500 gigabyte disk attached to your VM, you're running out of space, you don't have to shut it down and grow the disk and do a snapshot. You just say like, now it's 1,000 gigabyte disk, resize the file system, done, right? And you can do that live in production. You can do things like custom VMs where you can specify exactly how much memory and RAM you want, so you're not under utilizing your machines. There's a lot of these kind of nifty features that we offer that not many other cloud providers can touch. And that's really because we're building it on the same systems that the rest of Google uses, right? So our machine learning, data store, things like that, they're built to support Google scale infrastructure, right? So it can definitely support all of our customers as well, because we feel that everyone should have the best of everything, right? So why should only Google have these things? Let's open it up to the world. And so it's a pretty radical shift in how Google thinks, right? In the past, they would release a white paper and that's it. And then the community would go and implement it, right? So Hadoop is the canonical example of this. Google released MapReduce white paper and the Hadoop ecosystem blew up from it, right? But now we're seeing things like Cloud Data Flow, TensorFlow, things like that, where Google itself is open sourcing the application and then letting you run it on its cloud or anywhere else if you choose, right? But we really believe that our cloud will give you the best experience to run open source software like the stuff we're putting out.
So are you saying that the era of Google releasing these papers, like Google releasing their paper only when Google has something internally that is now better than the paper, or this kind of epoch of Google writes a paper on a service and then the open source community gets it implemented and usable, and by the time the open source community actually gets it usable, Google's got something new that they're using internally. Are you saying that epoch stands to end with GCP because Google will just gradually move towards a situation that is more and more parallel in terms of what the public has access to and what Google has access to?
I mean, as an individual, I certainly hope so. I think a lot of people have caught up to Google in terms of technology, right? Like in the past, no one else had these problems, and now everyone seems to have these problems, right? So it didn't make sense to release something like MapReduce because who else would need it? And then all of a sudden, everyone needs it, right? And if you look at something like HBase, so HBase is the open source version of Google's Bigtable. Now, internally, our Bigtable is still a lot more performant than HBase, but the APIs were slightly different. And so when we released Cloud Bigtable, we actually had to re-architect a few things to allow people to use the open source HBase API with our internal Bigtable, which if you look at a blog post, if you run HBase on Google Compute Engine versus running Bigtable, you get so much more performance using our managed Bigtable service versus trying to manage everything yourself. And this is our competitive advantage, right? TensorFlow, same thing. If you run it in our Cloud ML offering, you get that our huge superclusters without having to manage that infrastructure, right? So again, we're seeing our competitive advantage not in the implementation anymore. It's our infrastructure that really gives us that edge, right? So if you want to run TensorFlow on your GPU at home, go for it, and it'll work really well. And then when you want to run it in production, you simply run it on our cloud, right? And if you're not happy with our cloud, you can move off. And I think we're trying to be really fair in that sense. Look, the future now is no longer white paper and then see what the heck the community does. Let's just think open source from day one and do it that way. And I think TensorFlow, Dataflow, Kubernetes, gRPC, all these things really point in that direction where we want to be part of a community and not just Google from our high tower throwing down white papers, right? That's the old Google, I hope, personally. And the new Google, I think, is much more of a community-based thing. And Cloud Platform is definitely the biggest driver of that.
Well, and by moving the competitive moat from the software layer to the hardware layer, if the competitive moat is the actual infrastructure, then the economics become a little more transparent because Google gets massive economies of scale from having the infrastructure. But with software, there's not really an economies of scale thing. So like if I give you all the source code to my proprietary software, you can just run my proprietary software and I don't get anything out of it. But with Google, Google can say, okay, here's what we're doing with our infrastructure. And we're the only ones who can get the economies of scale because we're the only ones who are buying these massive amounts of infrastructure. I mean, obviously AWS or Azure might be also, but we are able to get these economics, and then we also have this software running on it, and we've got tons of experience. So it makes, I don't know, it's kind of a bright future because it's so much more transparent and win-win in terms of the consumer provider relationship.
Yeah, I do want to be clear that like there is a lot of proprietary software still going on. So for example, a good example is Dataflow, right? So Apache Beam is the open source version. And so when you write Apache Beam code, you can run it with a Spark backend, right? On your open source Hadoop clusters, you can just run Spark and it'll process Apache Beam code. Or you can run it on Cloud Dataflow, right? The same code can run on both. Now Dataflow, our internal runner, right? Our internal implementation of the Apache Beam runtime has a lot of secret sauce that we're not gonna open anytime soon. Instead, right? You can run it on-prem with something like Apache Spark. So this allows you to do something, so you're not locked in. I think the biggest thing here is we don't want to lock you into us for any reason, right? We want to compete on our performance and our price. We don't want to compete on, hey, you use our stuff, haha, you can never leave. And I think that's the big takeaway.
Okay, so like the APIs that I'm interfacing with, there are plenty of more. There'll always be an API. It's because like when I hear about DynamoDB for AWS, for example, I hear that I have no experience with DynamoDB other than I have heard that the APIs to it are proprietary. So if you use DynamoDB APIs with your application, you're locked into Dynamo.
Exactly.
But it's okay. So with Google, that sort of pent-up developer resentment will not exist because the APIs are just going to be like, it's SQL or something that's like much friendlier.
Exactly, right? So like that, we feel like that is not a good reason to pick a cloud, right? I picked this cloud because I have to. That sounds like a terrible value prop for normal people. I picked this cloud because it's the best, and that's what we want to compete on.
So, final question. I know we're up against time, but how do you see these different cloud service providers evolving? Do you see any sort of like, do you see more cloud service providers or fewer ones? Do you see specialization? How do you see like Azure and Google and Amazon and DigitalOcean, all these different things? How do you see them evolving in the future?
I have no idea. I have a ton of friends who work for Azure, a ton of friends who work for AWS. I think the future is bright for public cloud in general. I was having this conversation a few weeks ago at NGConf, actually. We were talking about public cloud versus on-prem versus private cloud and things like that. And I said, there's only going to be a few companies that have the economies of scale and the expertise required to do cloud well, right? It's going to make so what's going to happen is a startup is going to start in the same industry as an incumbent. You start using public cloud and just have such higher margins on whatever they do that they just start killing it, right? And then what do you do? How do you compete with that? You have to go public cloud. How long will this thing take? I have no idea. Am I biased? Of course, right? I work for a public cloud company. So that's what I believe. I believe public cloud is really the future. And so that pie is just growing astronomically. So there's a lot of pie to eat. And I think there's going to be a few players. Who's going to survive? Who's going to die out? I don't know. I really think Google's going to be in there for the long term. But again, I am super biased. But hey, I wish I could tell you about all the stuff we were doing internally. It would be amazing. I would also get fired. But just stay tuned. I think the next 10 years are going to be freaking amazing.
All right. Well, that's a great place to close off. Sandeep, thanks for coming on the show. This has been a fascinating conversation. I really appreciate it.
Thank you, Jeff, so much.